Hello students. Now today we are moving to the yesterday's extension part of the power MOSFET VI characteristics. So yesterday we have seen the 4-layer structure of n-channel enhancement mode MOSFET. So we have seen the diagram of the structure diagram of the MOSFET, how the different drain, source and gate connections are made, and how the current starts flowing inside the structure. Now I can show you how graphically the voltage and current can be explained with the help of this diagram called as a VI characteristics of power MOSFET. You can look at this diagram. So this is called as a VI characteristics. What you are observing on this diagram, V indicates the voltage and I indicates the current. But what voltage you are taking at the x-axis and what current you are taking at the y-axis. So I can show you here the two different voltages we are applying to the MOSFET, to the power MOSFET. Yesterday we have seen one voltage is applied across source and drain, and another voltage is applied across gate and source. Three terminals we are having in the MOSFET. There is a gate, source and drain. So in these three terminals, one terminal, that is a drain source terminal, is having the VDS. See here, I can show you. This is a VDS, voltage across the drain source. Remember this. Next, another one, voltage across gate and source. That one is a different. But at the x-axis we are taken the VDS, voltage across drain source, and at the y-axis I have taken the ID. So this is drain current. Why VGS is kept apart? Because this VGS now we are using to control the flow of the ID current. Drain current can be controlled. Controlled means how much from the minimum to the maximum current can be flow in the MOSFET. You are a person who can make, or we can have a control over the flow of the drain current in the MOSFET. So it is from minimum to maximum. That's why VGS is what we can say variable voltage. We are varying it as a controlling voltage. Now before going to see how this works, I would like to tell, here in this graph we are having the three main regions. So what are those three main regions? Now see here, this is one region. I can show you ohmic region. Second one is a active region. Third one is a cutoff region. So these are three main regions where your entire work is going to be taken place. Now first one will go, what is, or when you start giving VGS, and VGS is less than VGS TH into bracket, that is called as a VGS threshold voltage. See here, I am again showing you this. Here I have written VGS is less than VGS into bracket TH. So what is VGS into bracket TH? It is a VGS threshold voltage. Threshold voltage means it is a minimum voltage which is required to make your MOSFET turn on. So when the minimum amount of this threshold voltage is applied to the gate and source voltage, your MOSFET will turn on. But I am not applying it. So what I am doing, my VGS I am keeping it very less. Initially it is very minimum. So that's why I have shown with the lesser indication. VGS is less than VGS threshold voltage. So check it, what happens when your controlling voltage is very minimum, whether your current from the drain to source, that is ID current, is flowing or no. So obviously when the VGS is less than your threshold voltage, it is telling your MOSFET is in a off condition. So if it is in off condition, there is no flow of the ID, that is, there is no flow of the drain current. So that point is called as a cutoff region. So this is a cutoff region. Cutoff region occurs when your controlling gate to source voltage is minimum than the threshold voltage of the gate to source. Now what happens? Now you have to think about how to make the drain current to pass from the drain to source. Then you need to think you have to increase the VGS more than the threshold voltage. So that point will gives you to make the MOSFET turn on. So where it is there in this graph? So now see here, I will show you. This is a point where I have shown VGS is greater than VGS threshold voltage. Initially it was very less, now it is increased. So what happens? VGS controlling voltage is increases. So as soon as you will increase the gate to source voltage than the threshold voltage of gate to source, then it has to obviously drain current starts flowing with the help of this. Then obviously your MOSFET will turn on. So when the MOSFET will turn on, so that region, it is shown with the dot lines here, you can observe, that is called as a ohmic region. So now this is simple one. Last one is remaining which one? That is active region. Okay, you are seeing here active region. So what happens in the active region? So in the active region, there are a number of curves we are observing here. VGS1, this is one curve, VGS2, this is second curve, this is VGS3, this is third curve, and this is VGS4. This is a last curve. So how these different curves are coming, current changes here. So initially VGS1 is showing one curve. This is a curve which is a smaller one compared to the VGS2. So how this is coming? So it is simple. It is just like a, you can say, a tap what you are having in your home, water tap. When it is having a knob, when you initially from the slower to the higher, when you start increasing the knob rotation, the water force start coming high. So like this it is. When you are going to give a voltage across the gate to source, slowly minimum to the maximum, the current which is flowing from the drain to source of your MOSFET, it starts increasing. It is simple concept. So when your gate to source voltage, controlling voltage is minimum, your drain current is also minimum. When it is gate to source voltage is increasing, and then also here the drain current increases. So that's why they are shown here VGS1, VGS2, VGS3 all are up to VGS5. VGS5 is maximum than the VGS4. VGS4 is maximum than the VGS3 till the VGS1. So what happens here? Your drain current start increasing and increasing. The number of curves are changing here at the initial 1, 2, 3, 4, 5 curves are coming, and when they will becomes constant, they will show the straight line. So this straight lines on the curves, so these are area what it is having. This area is called as an active region. So in the active region, what happens? MOSFET acts as an amplifier. You might have to remember it. And the last one point that is remaining, it is, you can observe here, BVDSS. What is the meaning of this BVDSS? This is a drain to source breakdown voltage, we can say. Drain to source breakdown voltage. What is the drain to source breakdown voltage now? So drain to source breakdown voltage means you are applying the VDS. Drain to source voltage you are applying. Remember, the drain to source voltage what you are applying, it should not more than the BVDSS. So if it is crosses given one value of BVDSS voltage which has to maintain, if it crosses that voltage, your MOSFET may damage. Each and every components are having its limitations. If you cross the limitation, if you're applying a maximum power, maximum energy, so that's why automatically those electronics components will damage. So here also there is one limitation of giving the drain to source voltage. If you cross that, so here there is one straight line they are shown. This is a straight line. Here only it is a restriction is given. So in between, so within the range of this only we have to apply the voltages, and we can check across the VI characteristics of our power MOSFET. This is about the explanation of the VI characteristics of the power MOSFET.